Hi, my name is Alexander Knop, and this is Introduction to Combinatorial Game Theory. In the previous video, we discussed the game of Nim. In the following videos, we are going to talk about the way to think about all games like the game of Nim. In order to do this, we need a new notion, which is a notion of a game based on a graph. A directed graph G is a pair V and N such that V is a set and N is a function that maps V to the set of subsets of V. The game interpretation of this is very simple. It's a game where V is the set of positions and from a position x you can go to a position n of x. For example, in the game we considered in the first video, the set of position was the set of integers. Then V is the set of numbers 0, 1, etc. And from a position n, we could go to n-1, n-2, or n-3. So n of x was defined as the set of x minus 1, x minus 2, and x minus 3. But we need to make sure that none of these numbers are negative. So this is the rule for x greater or equal than 3. N of 2 is 1 and 0. N of 1 is just 0, and n of 0 is an empty set. Another notion we need is the notion of a Sprague-Grundy function. Let G be a graph, then a function G from V to the set of non-negative integers is a Sprague-Grundy function for G if and only if G of x is equal to max, and please do not confuse it with the maximum function, of the set G of y where y are neighbors of x. And max of a set S is the minimum of the set 0, 1, etc. minus S. In other words, max of S is the minimal non-negative integer that belongs to the complement of S, or doesn't belong to S, in other words. Let's try to find the Sprague-Grundy function for the game from the first video. Recall that V is the set of non-negative integers, and n of x is equal to x minus 1, x minus 2, and x minus 3. For x greater or equal than 3, n of 2 is 0 and 1, n of 1 is 0, and n of 0 is an empty set. So let's draw a table where we would write the values of the Grundy function. So 0, 1, 2, 3, 4, 5, and 6. Okay, the Sprague-Grundy function of 0 is 0 because it's a max of an empty set, and max is the minimal value that is not in a set, and 0 is not an empty set, so it's 0. Okay, now let's compute the Grandi function for 1. N of 1 is 0, so we are interested in the max of the set containing 0, which is 1. Okay, what about 2? For 2, we have two neighbors, 0 and 1, with Grandi function 0 and 1, so we are interested in the max of 0 and 1, which is 2. Okay, for 3, now we have three neighbors, 2, 1, and 0, with the Grandi function 0, 1, and 2, so we are interested in the max of this, which is 3. Okay, finally, for 4, we have three neighbors, 1, 2, and 3, and we are interested in their max, which is 0, because 0 is neither 1, nor 2, nor 3, and it's less than all of them. Okay, for 5, you have 2, 3, and 0, and their max is 1. And for 6, you have 3, 0, and 1, and their max is 2. So now you can see that there is a pattern, 0, 1, 2, 3, 0, 1, 2, and 3, and so on. And like in the first case, we can prove this pattern using induction. One may notice that the value of the Grandi function is 0 where we had p positions. And this is not a coincidence. One may prove the following theorem. So if you have a graph G such that every position is either p or n position, then there is a unique Grandi function, and x is a p position if and only if g of x, the Grandi function, is equal to 0. In this video, we studied the Grandi function. In the next videos, we are going to learn how to apply it to a wide class of games. If you have any questions, ask them in the comments. See you later.